And today we'll talk about the continuation of the lecture on last Thursday. We'll transition from a general concept of the ISA and how do we represent your program, right, into assembly. And in particular, we'll talk about x86 assembly. Today we'll talk mostly about the one of the most basic type of operation is assembly, which is compute operation. And to do that, let's do a quick recap. Sorry for slashing the slides. Last Thursday, we talked about code example, right? Where you can have this main function. It does nothing except for assign 0 to A, 5 to B. And then I would return A plus B, which is the results of the computation. If you compile this code, you can have some file name .o, right? This is the object file. You can do object dump -s, which would give you the assembly code of the result of the compilation. And from this, right, what we developed on last Thursday is that you can have the notion of the main function, right? And here is the address of the main function, 5FA, right? And to follow up one of the really interesting question by one of you on Thursday, right? There's a question about, is this going to be 5FA every single time I run this program? And the beauty of how you manage the computer is, from the programmer point of view, is 5FA. Inside DRAM itself is another location. And the machine has a system, it's called virtual memory, to tell when I have a pointer to this 5FA for this main function, where exactly is the location of this code in DRAM. What you see from the programmer is going to be 5FA, and that's totally okay. The computer really have the method to translate that and know the actual location of that line, that instruction, right? And now that you have the function body, right, the rest of the instruction inside the function body has its own address as well, where you can see from the left side here, this is where the assembly code inside the virtual address space, right? That's how you can translate into the physical address. And these are the address of each line in here. The number you see in the middle are the actual binary for that instruction. Basically, it's what represents each instruction. This is what the computer actually sees. And on the right side is the assembly code that represent the instruction itself. For example, what I circle is I want to add EDX into EAX and write the result into EAX. That's how x86 works. You can see that there's a binary representation of the add instruction, right? These are actually what the computer see, and if it sees 01D0, it knows exactly you want to do an add EDX EAX. And with that, we kind of summarize that there are three main types of instruction. One is compute, the other type is memory, the other type is called control instruction. Today, we'll talk about compute and memory instruction, and then we'll follow on Thursday about control instruction. How do we implement if, else, or for loop? And with this, right, a quick recap again from last Thursday is, these are the opcode. It tells you what exactly, what are you supposed to do with the instruction, right? And then there's an operand part where it tells what are the data involved that actually has to do with the opcode. All right. And then we also talk about this concept on the notion of register, right? The register are extremely fast but small temporary unit of storage that's inside the processor, and they are visible to the programmer. Why do you need a register? Let me ask you this. How many people write a program, right? Let's say you write a program and you have to declare some temp variable like int I and j, right? Oh, sorry. let's say you write a program and do int I and j, and you use I and j for some purposes, and you sometimes reuse it actually. How many of you write a program this way and you create a temp variable? All right, yeah. So many of you did, right? And one beauty of software programming is there a limit, to be honest? Like, is there a limit to how many temp variables that you can have? Can I have 1,000 different temp variable? I mean, can you declare that, right? Is it good to have, or is it good to have? It's not good to have that many temp variable, but can I declare that? Can I add more temp variable based on my demand? If I need more, I'll just add more. Can I do the same thing with hardware? Let's say I buy a CPU, right? I go to a computer store and say, hey, I want an Intel CPU. I got the CPU, and somehow I say, I need more temp variable. The number of registers is not big enough. I want to add more. Can you do that? Right? And as the chat said, you can allocate as big of an array as possible in the memory. But if I want a temp variable stored in your processor, can I keep adding? After I buy the chip, right? Can you modify the hardware? No, right? In most cases, unless you're dealing with programmable hardware, no. Which means that every single chip would come with some amount of temp variable. Why is that the case? So that programmer can use it, right? So that programmer can use it. And the compute instruction would directly access this temp variable inside your register, right? So that you can do computation. And another terminology we kind of talk about on Thursday is register file is as simple as a group of register. Like the register that you have in the CPU, that's called the register file. And you might be now curious, like, okay, but these are memory, right? These are used to store my data. So what's the difference? What's the difference? One big difference is registers on the CPU tied to the ISA, right? If the ISA or x86 manual said there are 16 register, it's gonna be 16 register in the CPU. Unlike the memory where you can keep adding, or you can have the Intel processor that backs up 16 gigabyte of memory, 32 gigabyte of memory or more, right? You can extend that. And register are really, really, really fast, right? If I want to access the data in the register, it's like, say I want to make coffee, right? If I want to make coffee, the first place I would look is into my kitchen cabinet and see if I have coffee. So think of it as my register is right there. If it's not there, then you go to the memory. It means that I have to drive out and buy it from, I don't know, Big C Lotus or somewhere, right? Somewhere not close by. Same analogy apply here. Register is small, it's fast. Memory is huge, but it's bigger, right? And there's a strict limit on how many register that the programmer can use. In Intel x86 processor, there are 16 of them, for example, and you have to somehow manage with just 16 of those, right? There's also a special register called the program counter, right? Why are they special? The purpose of the program counter is it tells the CPU or the hardware, even the GPU has this too. It tells what is my current line that I'm running. So it basically allows the hardware to know, okay, this is the next line, and this is the next line. This is what I should do next, right? And typically this get incremented every cycle. Typically, I would increment the PC every cycle. Why is that the case? The way you write a program, you also run line by line by line by line, right? So that's how the PC get incremented because we assume the programmer would write in a language that run line by line by line. Sometimes if you read textbook, you might have, actually today in the slides, I sometimes use instruction register because in the Intel processor, these are called instruction register. It's the same thing. It's a program counter. All right. And now that we talk about the register versus memory, let me draw a little bit more of the difference, right? I can have the input and output I/O in the red box, the memory in the green box, and the register, anything that has to do with the processor on the blue box. So what boxes of color should my register be? I have a register, it's going to be in somewhere in the processor, right? It's actually called the data pad, which is not inside the control unit, but it contains, the data pad will contain anything that has to do with your data inside the processor. The PC, program counter, and register are going to be there. Then if you have pointer access to the memory, it's going to be in these green boxes, right? And then if you write a program that do printf, scanf, for example, if you do scanf, there'll be an input coming in so that you can do scanf, so that it's fed into the memory, which then get processed by the CPU, which would get control so that if you do printf afterward, right, it get display on the output. And the control unit is there to kind of control every component so that the computer run, right? So that's kind of like really, really, really high level overview of this, right? We'll go into more detail into the future classes, but here's a really high level overview. And now that we know about the content of where the register belong, let's zoom into just the x86 64. And as I said, right, there are 16 registers. The first 8 is named RAX, RBX, RCX, RDX. And then there are 4 more that use for special type of data. RSI, RDI, these are source and destination index. RSP, RBP, stack and base pointer. These 4 will see more. RSI and RDI will see more with the dealing with inputs to your function call. RSP and RBP, you will see this more when you have to manage the function call. So save this a bit. We'll talk about this RSP and RBP more in the not next lecture, but the lecture on next Tuesday. Then there's R8 to R15, right? At some point, Intel was like, okay, let's just name it with number. Make much more sense, right? If I want just 1 byte, so let me ask you this. If I have a 64-bit machine, how big is 1 word for the 64-bit machine? How big is the data word? 8, right? It can go up to 8. So let's say I have a long integer, it can go up to 8 bytes. Byte 0 to byte 7, right? So if I type in AL, it's gonna just refer to the first byte, whatever is here. So this is AL. If I say AX, this is byte 0, this is byte 1. AX is basically this region. 0 is on the first byte, so this is AX. If I type in, right, EAX, it's gonna cover 2 more bytes, byte 2 and byte 3, right? So there's gonna be this range. Okay, so this is EAX. And when I refer to RAX, it's the entire thing. This basically allow you to access data in different granularity. I want 1 byte only, just use AL, right? More efficient. You don't have to transfer the entire 8 byte around all the time. And then there's a student actually asking the question about why do we name it RAX, RBX, right? Anyone wondering why don't they call R0, R1 to R615? Doesn't that make a lot more sense? Right? Why do we even name it RAX and RBX and RCX and then somehow switch to R8, R9, R10? Yes, exactly. Each letter here in the historical context, right? Back, I think probably a long time ago, actually. There are historical reasons for these names. A is accumulator, B base, C is counter. So every time you use counter, typically they will use the C. Data, when you want to store the data, you would either use RAX or RDX. So those are more common. D and RSI and RDI is source and destination index. These are typically used when you have the input variable into your function call. There's also a stack pointer and base pointer, RT and RBP, and at some point, everything else like R8, R9, and to R15. These days, in modern day computing, you can use these interchangeably. What I would avoid is using RSP and RBP, but the rest, they are what we call general purpose register. Use it for any purpose. All right, so that's a historical reason. Why are they keeping the name? Anyone want to take a guess why they are keeping the name? Why don't they rename it to R0, R1, R2, R3? So what would happen if I have a program that compiled a long time ago and I actually lost the source code already? I have some binary and it's written using RAX and RBX. What happened if I change the name? If it's written in assembly, it might not compile into the correct binary, right? So that's one of the reasons why they might have choose to keep the name. I mean, you can do transformation as we discussed earlier on Thursday, but most the decision from the team that designed x86 is like, okay, let's keep this name. Everyone is used to using this name already, right? Yeah, one reason. It almost because there are multiple reasons with this, right? When you write a program for x86 or when you write a program ever, right? You want to sell your program, so you will try to target the ISA that most people use, right? So that's why you have a lot of application developed on the premise that it's going to be run on a computer that uses x86, right? And that's how when you keep extending, you can still run old application on your computer, right? Because they want this backward compatibility. You want to make sure that old programs still run, right? It's a big thing. You bought a program already. It costs a lot of money. So you want to make sure it still run on a modern machine. So this is another reason, right? Any other questions before we talk about how do we move data into a register? So there's an instruction that are being used to move data around, and the instruction is called move, M-O-V, right? Move can be used to move the data from the memory to the register or from one register to another register. It's pretty flexible, right? And this is how it works. You can do move queue. Move queue is moving an entire 8 byte of data, but you can change it with B, W, and L for different granularity of like 1 byte, 2 bytes, or 4 bytes of data on no suffix. It's move. Move queue, source, destination. Source means that's where the data comes from. Destination is where I put the data into. And the reason why I said move is flexible is source and destination can come in different format. It can be a flat constant, a constant in hardware language we call constant immediate. Immediate basically means that's a number and treat that as a number. To specify something is a constant, use the dollar sign. Whenever you put a dollar sign next to something, it means that's the number. You can put register in the source or destination. You can put a register name there as well. You treat the register as what you want to move from or to. Or you can use a combination of memory and register. So this might look confusing for now. So let's go through some examples. So hopefully this is much more clear, right? As I said, move has to do with source and destination, right? The source can be number, the immediate, just any number. It can be register, and it can be memory location, some address. Destination, you can put the data in either register or memory. And let's go through these examples one by one, right? So let's say I have this first instruction, move 0x4 into RAX. This basically means that, let's say RAX is temp, I do temp equals 0x4. I move the data 4 into RAX. I can use immediate and memory. Move literally -20, but the address where RAX is pointing. So now treat RAX as a pointer, that's an address, and put -20 right there. Right, so P is RAX, star P is parenthesis RAX. When you put parenthesis onto something, these become the address. Whatever is inside the parenthesis becomes address. So treat whatever RX represents. So let's say RX is 40. You would go to address 40 and put the value -20 at address 40. You can have source being a register, destination is a register. In this case, right? In this case, A is R10, B is R9. I put the value R9 into R10. I can do register to memory. Now B is R9, A is R10, but instead of putting that into R10, I put this value R9 into the location where R10 is pointing. So let's say R10 is address 40. You would go to address 40 and put whatever value is R9 in that address. You can do move memory to register. In this case, B is R9, A is R10 from the assembly code. You would go to address at R9. You go to address at R9. See what's the data in there. Put the data into register R10. Any questions? So basically, this is how the move instruction works. You can the overall goal of the move instruction is to move the data around. You move the data from register to memory, memory to register, some flat immediate constant data to a register, or just write a value to an address, right? And now we talk about the address. There are multiple ways to refer to a location in DRAM. We call this addressing mode, right? The addressing mode is how do we obtain the operand that govern where is the address. And in this slide, I'm going to use more generic term. It's not in x86 format because it applies to most languages. It applies to ARM, it applies to RISC-V, because there are only a handful of ways you can address the location in the memory. The most obvious one is called absolute addressing mode. I want to load whatever value is in address 10. So now the number becomes the absolute value. Go to that address, put the value into R0. So that's called absolute addressing mode. You can do register indirect, where you treat R1, in this case, as an address. So this is an address. And you go to that address, whatever data is there, put that into R0. You can do a display space. Display space is similar, almost similar to register indirect. So you start with R1, but you do R1 plus offset. So whatever R1 represent, treat that as an address, and you add the offset, write it to R0. And each of the ISA, basically ARM, x86, RISC-V, MIPS, right? MIPS is the ISA that, how many of you own a PlayStation 1 or 2? I don't know. Actually, I'm not surprised if you didn't own it. It's a long time ago. Yeah. So for those of you who have PlayStation 2, for example, it uses an ISA called MIPS, right? MIPS is the, anyone here heard about this ISA called RISC-V? So this is basically, you might not have heard about it, right? But definitely you heard about ARM and the M1 processor that Apple is using, right? And also the x86 that Intel is using. From more like a startup perspective, and also like company that do hardware, in these days, some actually a handful of company also looking at RISC-V ISA because it's totally open, completely free, and it's actually good. It actually can compete with the modern ISA. RISC-V is like the modern version of MIPS ISA. That kind of like being developed into the current version of RISC-V. And if you do research in architecture, for example, is one of the ISA that you might need to be on a lookout for. There might be companies that develop chips based on this ISA. But each ISA, going back to the addressing mode, each ISA would define, it would have the definition of how to address, right? How to search for the address. So what you would do is you go read the specification. In particular, there'll be a section that talk about addressing mode. It would explain how do you access your data. So why do we have different addressing mode? Because sometimes you don't know the address, or sometimes you cannot represent the address using all the bits that you have, right? So one thing you can do is to store the address in a register so that you can store a 64-bit address. Then you use that as an address, right? You can also write a loop and in a way that you can use the same base over and over and over and just change the index, right? How many of you write a loop this way? For I equals 0, I is less than n, I plus plus, and inside the loop you do a of I equals something like a of I equals 0. How many of you write a code that behaves something like this? You loop around and you go through an array. It's super common, right? So in this case, what the compiler typically do is A0 become the base. I is going to become the index that get incremented every cycle, and you use the addressing mode, right? That would do base plus index. So you can fix the base all the time, and you just increment the index, and you can load, or store, basically put the value into these increasing address. So let's go through some example of the x86 64, the modern Intel / AMD processor for the addressing mode, right? The format is this: displacement in parentheses, base, index, and scale. This basically means what I do, RB can be like the register name, like EAX, RAX, for example, right? Register name. RI is also a register name. So let's break this down. And then S is a number that can range from 1 to 4 and 8. D is a flat constant number. So let me give you an example. If I write in 10, in parentheses, %RAX, %RBX, 4. These basically, let's say, give me a value for RAX. Can someone give me a value for RAX? Let's assume any number. 47. How about RBX? 6. All right. So my address, ESS, sorry, I cannot write. It's going to be 10, the displacement, plus base, which is RAX, plus RBX multiplied by 4. So it's going to be 10 plus RAX, in this case is 47, plus RBX multiplied by 4. This is 6 multiplied by 4. So that's going to be 57 plus 24. So my address is 81. My address is 81. And that's it. That's how you compute the address, right? You take the value of RB. Whatever value of RB, the base, in this case is RAX, that's 47, multiplied by scale plus the index. Index is 6, so it's 4 multiplied by 6 plus the displacement. So let me give you another example before we take a 2 or 3 minutes break so that you can go through this example and tell me what's the address. All right. So let's say I want to access the variable at this address. 0x10 %EAX %EBX and then 4. And then now EAX is 0x12, EBX is 0x4. What's my address? All right, so let's do 4 minutes break. We'll come back at 2:45. We'll come back at 2:45 and we'll compute this address. All right, let's do some quick exercise here. And once we're back, please tell me what's the address. All right. All right, now that we are back from the break, can someone tell me what's the address here? Yes, exactly. 32, right? 0x32. Why? This is basically 0x10 plus 0x12 plus what's 4 multiplied by 4? That's 16. 16 is 0x10. This is basically 0x32. All right. So that's how you can compute the address and use move instruction. Now that we know about the move instruction, let's write a program. Big step up. So let's write a program that would swap two numbers, x and y. Right? I have x and y as a pointer coming in. I would swap x and swap y. Based on the code I show here, I would have temp1 equals star x, temp2 equals star y, x equals temp2, y equals temp1. And let's assume that the variable x is in RDI, y is in RSI, temp1 is in RAX, temp2 is in RDX. How do I write this function? So I'll write the first line, you finish the rest, right? The first line is I would do move q. I want to move what into what. I want to move the data at x. X is RDI, but I want the address. So I would do move q in parentheses RDI. I move it to where? Temp1. I say temp1 is RAX, so I put this into percent %RAX. So that's the first line. How do I do temp2 equals star Y? Can someone tell me what is star Y? What is Y? What is Y? Look at our assumption. What is Y? RSI, right? So how can I get the address where RSI is pointing at? What do I write here? Put in the bracket, right? Parenthesis percent RSI. What's my destination? What do I write it to? I want to write it to temp2, right? So what do I put in? Percent RDX. We are done with the second instruction. The third one is I want to make sure now X store temp2. What is temp2 right now? Temp2 is RDX, right? I want to store this data into star X. What is X? Yeah, star Y dereference, right? Yeah, that's what I mean by I want to access the data that point to by RDI. So RDI is a pointer. RDI is a pointer. Is it more clear now? I want to make sure that's clear. RDI right now has an address. Okay, perfect. So in this case, how do I get star X? I have RDI, which is X. Right? But I want to swap. I want to do X. Oh, not my bad. What is RDX? RDX is temp2. When I want to put into star X. What is X? All right. So should I put in RDI or RSI? Look at the code. Which one is correct here? RDI or RSI? It has to be an address, right? Is that RDI? Yes, RDI. Thank you. And then the last one is I want to basically move Q, right? Temp1 is RAX. And I want to move it to percent RSI because that's Y, right? And that's all. Basically, with this, I can swap to number, right? I can swap to number. So now this is a move Q instruction. The other instruction that kind of related, but it's not moving anything is what if I want to just compute the address, right? What if I want to compute the address so I can use it later? I can use the instruction LEAQ. LEAQ would take source in this format, the base, index, and scale, like the addressing mode, right? Source would take instruction in this format. And you can put this in some other variable. So the usage of this is to compute the address. I want to compute the address and store that, right? Store into a register so that I can use later. There's a question, is moveq for assigning value? Moveq is to assign value and to move data around. So you can move the data from register to another register. You can move the data from register to the memory. You can move the data from memory to the register. And you can move the data from a flat constant number to register or to memory as well. So it's used to assign the value to the destination. And the value you're assigning is from the source. Is it clear? Basically assign the value at the destination based on the source. And, so, sorry, there's no response. Is it clear or is it not clear? All right, awesome. So now LEAQ is different. LEAQ want to compute the address. This is basically the same as I want to compute the address of something, right? This is the getting the reference. I want to compute the address. So that's one use of LEAQ. The second use that a lot of compiler, including GCC, do is if you have any arithmetic operation, has nothing to do with the address, but it's arithmetic operation that follow this format, x plus k multiplied by y. Compiler would optimize your code using the LEAQ trick. This is the trick that computer do. So let's have a function in C over here, right? Take in x as an input. What does this function do? Can someone tell me what does this function do? Input multiplied by 12, right? It's simple. But one thing I noticed is that x multiplied by 12 is multiplied by 12 is essentially it's the same as x plus 2 multiplied by x multiplied by 4. Why? It's 3x multiplied by 4. 3x multiplied by 4, that's 12x, right? And because the x plus 2 multiplied by x is in this format, right? You can write it here. Temp equal x plus 2 multiplied by x. It's going to result to 3x, right? So what if you do 3x left shift by 2? What's the result? What is 3x left shifted by 2? What does left shift by 2 do? It's multiply by 2 to the what? This is the same as 3x multiplied by 2 to the something. 2 to the 2 is 12x, right? It's the same function. And because I realize that it's in this format, x plus 2 multiplied by x, I can do this, LEAQ, RDI is x. I do x multiplied by 2 plus x. This is x multiplied by 2, wait, plus x, this is going to be 3x. I put 3x into RAX, and then I shift left, SALQ is shift left by 2. This is going to be the same as multiply by 12. Anyone wondering why do I go through this effort to avoid multiply? Anyone are wondering that? Can you tell me is why anyone puzzled by why do you have to do this? So let me ask you this question, right? If I ask you to add two number and I ask you to multiply two number, which one is faster for human? The add is faster, right? You can just use the two number and you can add them. Multiply involve multiple steps. The step it actually involves multiple add, to be honest, a lot of add, right? So in your computer, multiply take a longer time. So if the compiler GCC, for example, detects that this is what you try to do, it will break down and use this trick to make it faster. To make the multiply faster by instead of multiplying, use this LEAQ instruction followed by shifting a lot fast. Well, quite a bit faster, right? And your compiler, GCC, would apply tricks like this to many things, to many parts of your program, so that your program would, by some magic of the compiler, run faster than you would have directly translate, right, the program into assembly. All right. So what else, right? These are common arithmetic operations available in x86. Self-explanatory, to be honest. Add, subtract, multiply, shift left, shift right, logical shift right, XOR, and or, increment, decrement, negation, and not. Right? So these are self-explanatory. The meaning is to the right here. Add, for example, is destination equal destination plus source, right? Most of the time you don't have to remember this, but it is good to know and to be able to guess what the instruction is doing. On the exam, for example, there'll be some reference guide for you to let you know that, okay, these are the instructions and this is what it's supposed to do. You just need to follow that instruction, and it should be doing what is defined. All right, it should be doing what is defined. The next thing that we need to give to the programmer. How many people like the fact that we can debug something? How many people use GDB at all for your assignment too? Or use like printf in the middle or something? You use printf, right? So for those of you who use GDB, did you realize that also how many people write code in Python or Java and use the debugger where you can run and you can go step like line by line by line by line? Anyone use an editor like that? We use it all the time, right? How many people are wondering, how can I give you that ability to pause in the middle and see what's going on without actually resume the program run, right? Without actually resume the program, I'm gonna pause it. I take a peek at each variable, right? So one thing that the hardware is supposed to give it to you is what we call processor state. A processor state. So what does states mean? It's a status, right? It's a status of the processor. What's going on? What's going on with the value that inside the processor? These are what's visible to the programmer. Programmer can see what's going on and can control that. So what are visible? What can be seen by the programmer? And to be honest, there's a lot of things that we hide. Right? The people who built the CPU would hide from the programmer. For example, what goes into this wire? You not need to do you to know that. But there are certain things that would be good if we can expose it to the programmer. What are these? Any value stored in the register, you can access them. The runtime stack. So if you use GDB before and you have seg fault, right? Anyone run into segmentation fault already? How many people hit it when you run into segmentation fault? I see like a party emoticons. Yeah, assignment 2 is just flooding of multiple seg faults, right? That you would get used to, and you hopefully get used to how to deal with it. You can use the runtime stack. This would track the function calls that are going on in your program to determine what's going on with your code, right? So these are also the processor state. You can look at the instruction pointer. Why? We can tell what line we are running, right? This is again the same as program counter. It points to the next instruction so that you can check and debug your program. It also has the status of the recent instruction through what we call condition code. We will now expand the concept of condition code. Condition code typically in the x86 processor like Intel or AMD, there's a carry flag. The carry flag was set to 1 if the previous instruction results in a carry. Can someone tell me what is a carry? When you do math operation, what's a carry? If you add two number, and what would happen if we say, hey, the add has a carry, not carry, it has a carry. Yeah, that last digit, right? When you add the two number, and let's say the last digit adds up and is greater than 10, then you have the carry. Same concept here. Carry basically means it carry into the extra bit that doesn't fit the line. 0 was set to 1 if the previous instruction would result in a 0 value. So I hope this is clear. If I do something and it results in a 0, the 0 flag would be set to 1. Sign flag is if I do something and it results in a negative value, set that to 1. Right? If I do something and it results in a negative value, set that value to set the sign flag to be 1. Overflow is when the executed instruction results in an overflow has too many bits that you can capture. Overflow flag would be set to 1. And these flags are set automatically on arithmetic instruction like add, multiply. Certain instruction doesn't set this flag like LEAQ, but most instruction would set the flag. Anyone want to take a guess on why do we want to know the flag? Error handling for sure, right? If it's overflowing, you might want to check, hey, is something overflow? Does my number too big, right? What else? Who write code that has something like this? Who write code that do if x is less than y, do something? It's everywhere, right? We do this all the time. Or if you write the code that say if x equal 0, right? You can then do a compare instruction, the compare instruction, to compare the two number. The compare instruction would set the flag. This compare instruction would set the condition code. So let's say you want to compare x and y in here. Let's say x and y, x is in EAX, y is in EBX. You can do compare CMPQ, EAX, EBX to compare the value. And it would set the flag accordingly, right? 0 flag would be set if source 1 equals source 2. Sign flag would be set if source 1 is less than source 2 because it results in a negative number. Carry flag would be set if there's a MSB carry out because you basically this operation would actually do source 1 minus source 2. So if there's a carry flag set by this subtract operation, you have the carry flag. Overflow looks cryptic, but the key here is overflow the two complements format. It overflow the two basically overflow to complement formatting, right? And now that you can compare, you can basically then use an instruction called jump. You can use an instruction called jump. We are not going to go into the instruction called jump in the next slide. It's coming up the next 2 slides. But now you can compare the two number. The comparison will set the flag. Compare will set the flag. Another instruction is called the test. The test instruction. This tests the flag. This can test, set the condition code, but it's not compared. So CMPQ would do source 1 minus source 2. Test would do source 1 and source 2. This is logical. And. So instead of subtract, now test would do and then put the condition code to the register. Carry, overflow, based on source 1 and source 2. Right? Then you can also manually set the condition code. Let's say you somehow want to set the condition code by, I want to set 0 flag to be on. You can do set E. Or set S would set the sign flag, for example, right? So you can use this in tandem, in combination, to do something like this C code, right? I want to return X greater than Y. So that's the only thing I do. I want to check if X is greater than Y, right? I want to check if X is greater than Y. Let's break down this code and do it one by one, line by line, all right? Any question about the C code, I have X as an input, Y as an input. I return X greater than Y, which basically check if X is greater than Y or not. Let's assume X is in RDI, Y is in RSI, and return value is stored in RAX. So what you can do is, I would first compare RSI and RDI. I would compare RSI and RDI. But because I then need to actually put the result, because I want to return, right? I want to return the value and return the result of this X greater than Y to RAX, right? To RAX, which means I have to do the set operation. The set would store the results into the register. AL is the first byte in RAX. Now you store the condition code into RAX. But the set operation, the quick note is, it only set the lowest byte. So you would use AL, right? Now you have this is RAX. This part is AL. The condition is stored here. What happened to the rest? The rest here are just some junk value that we don't use. The safe thing to do is to clear the rest here, clear to 0, right? So if you use RAX later, it's just your condition code with a bunch of 0. To do that, you can use move CBL, which set the upper 32 bits to 0. That's why you have the last instruction, which is the move CBL here. Right? That's why there's a last instruction, which is a move CBL here. But this code is basically what it does is, I'm going to return if X is greater than Y or not. If X is greater than Y or not. All right. And now that we have the condition code, we can do something like, if X is greater than Y, do certain things. If not, do something else. When you have if-else statement, it means that your code can jump around. If I have the code that jump around, what I essentially do is I change the instruction pointer, right? I change the instruction pointer. Why is that the case? Let's say I have if, right, X greater than Y, else, right? And let's say this line is address 10. This is address 9. Over here in else is address 70, right? So when I do X is greater than Y, my instruction pointer is at address 9. If this is true, what is the next value of instruction pointer? So before I go into the condition check if X is greater than Y or not, my instruction pointer is at address number 9. What I'm telling you next is if you go into the if, you go to address 10, otherwise you go to address 70. In this case, what are the two options that my instruction pointer can have for the next line? What are the two different addresses that I can have for the PC, for the instruction pointer? So currently I'm at address 9. The PC is at address 9. I'm trying to figure out, do I go into the if or do I go into the else? If I'm going to the if, what's the PC? What's the next instruction? Where is the next instruction? Is it address 10 or is that address 70? If x is greater than y. 10, right? But if that's not true, what should be the program counter? 70, right? So now you have what we call code branch. Code branch. If this is true, go to the next address. If this is not true, go somewhere, right? This is called code branch. And it's a modification of the instruction pointer because instruction pointer points to the next instruction, right? And this can be used to alter the flow of the instruction, like when you have if else or for loop. For loop is kind of like if else, right? If it's true, you go back, do the loop again. If it's false, you go to the the next line of code out of the loop. You go out of the loop or you stay in the loop, right? And in hardware, in your CPU, the way this is implemented is we just need to update the program counter or instruction pointer so that it has the correct instruction, so that it points to the correct instruction. And the way we do this is now we know how to compare, right? We know how to compare. We also need to know how to jump. Jump is, let's say in that if else, right? In the if part, it's fine. You go to the next line. But if you go to the else, right? If your program has to go to the else part, then you have to jump somewhere, right? You have to jump somewhere. So over here, you have to jump instruction that has multiple condition. Basically, you can compare. You would first compare, and then you add the condition at the end. Jump, JMP is always jump, right? Always jump. JE is jump if and only if the zero flag is on. If and only if the zero flag is on, right? Jump if equal. Jump if not equal. Jump sign, jump if the negative flag is on. Jump not sign, jump if it's positive. Jump is greater than or equal, less than or equal, right? Jump above, jump below. So this is how you can control your program in tandem with condition check. Like if x is greater than y, if x is equal to 0 or not, you would use compare, then jump. All right, you would use compare, the compare instruction, then the jump instruction. And the JMP, the jump always, right, it's the same as a go-to instruction. And you can use this combination to implement, right, to implement what we call a loop on if else. And we're going to cover this in more details on the lecture on Thursday. All right. So on Thursday, we'll kind of come back and resume about how to deal with this condition code and jumps. For now, I want to give you one more example about what if I want to do conditional move. And we will break this down, right? It's one big slide. So I'm going to do one by one, line by line. Hopefully it helps with clarity. Conditional move is something like, it's a move instruction, right? It's the same as move. You want to put data somewhere, but it's based on condition. Move based on condition. For example, in this case, our conditional move is move only less than. Move only if less than. All right. We can use this to implement some simple if-else statement, and there are certain performance benefit. This can be done through what we call conditional move instruction. So let's look at the C code first. Let's look at the C code. Over here, right over here, what does the C code do? I want to compute absolute difference. I have two input X and Y. How do I compute absolute difference? Can someone tell me what I want to do this? Absolute of A minus B. That's all. That's all I want to do. Is it clear? For the purpose of this function. So the way I can do this is if X is greater than Y, I'm going to return X minus Y. If X is less than or equal to Y, to get the absolute value, I would do Y minus X, right? So that the number is always going to be greater than 0. That's how you can compute absolute. All right. Are we clear with the C part? So the C part, I hope it's clear. If it's not clear, let me know. Basically, it's computing the absolute of X minus Y. The right side, I assume that X is in RDI, Y is in RSI, RAX is the return value, right? So now let's go through the assembly part. What does the first line do? Can someone tell me what does the first line do? So what's RDI? What is RDI? It's X, right? So the first line is basically, I first to say RAX is gonna equal X. Then I do subtract. Subtract RSI, RAX. What does this mean? I want to subtract what to what? What is RAX and what's RS? What's RSI? Y, right? And what's IX right now? What is RAX right now? RAX is X, right? So what you do is RAX is going to equal to Y, Y minus X. Y minus X, right? Because I subtract RSI, Y, by X, which is RAX. Then the next line is what? What is RSI? RSI is Y, right? So now RDX equals Y. Then I subtract again. I subtract RDI. What's RDI? What's RDI? RDI is X, right? So RDI is X. So over here, I do RDX equal to X minus RDX. What is RDX? That's Y. So do you see by this line, so let me actually draw this, right? By this line, RAX has what? And RDX has what? So what's in RDX? So from the first four line, right? RAX is going to be Y minus X. RDX is going to be X minus Y. Is this clear? Yeah, so RAX is going to be Y minus X. RDX is going to be X minus Y. What should we return? So let's say the return value is RAX, right? How can I make sure that I return the absolute value? I would have to check, right? If y is greater than x, I'm gonna return rax. If, yeah, basically check the bigger ones. So I'm gonna check the bigger ones. Basically, I will compare RSI and RGI. I'm gonna compare RSI is y, RGI is x. I would do this comparison by I do y minus x. I would do y minus x. If it's less than or equal to 0, what does it mean? Because I want to do less than or equal to 0, right? What does this less than or equal to 0 mean? If I do y minus x and it's lower than 0, it's a negative number. So you want to return what? The positive one, right? So in that case, if it results in a negative number, you put rdx, which is x minus y. If y minus x is a negative number, return x minus y. Where is x minus y? Where is x minus y? X minus y is in rdx, right? So you would do move rdx into rax, so it's become positive, right? Oh, okay. So great question. Why is the condition not x greater than y? So in computer, right? In your computer, the easiest way to do x minus y, I mean, the easiest way to check if x is greater than y or not is to subtract the two numbers and check if it's less than 0. Let me put it this way. So is it more clear? So you can for sure build a logic that would check x greater than y. But you can check this by doing x minus y and check if this is greater or equal to 0 or less than 0. All right. So what do you mean by top to bottom? Just want to be clear. Oh, you mean the code to the left, right? Yeah. So this is a more optimal version. The reason behind this is what we just did, right? What we just did. This is if else. And what I told you about if else is you probably most of the time you tie this with a jump instruction, right? You jump somewhere. The problem with jump instruction is it does take time compared to this straight line code. This is the optimization technique we call predicated execution. We replace if else with a straight line code that doesn't really have an if else. It doesn't really have an if else. Because why, right? Let me go quickly. Hopefully within 5 minutes, I'll tell you why. This is a common trick that ARM assembly, x86 assembly, and many assembly language, including the one on the GPU, are using. Why is that the case? In our CPU, right? When you update the program counter, because if you have if else, right? If else is you need to figure out, do I jump or do I not jump? Do I jump or do I not jump? Right? Based on the result of the if condition. The problem is in modern processor, you don't know whether you're gonna jump or not later on. It's not straight away, right? Which means that you need to wait until you figure out what's the next line that you have to run. If you can get rid of that, you can run the next line right away. So basically, this is optimization. It's called predicated execution. And predicated execution typically for small if else is faster. So your compiler always try to do this if it detects that if else is like one line long. right? So it used in ARM CPU, x86 CPU, and even the GPU for different purposes. For the GPU is different. For the GPU is different, but it's another form of predicated execution, or at least that would what I would classify it into, right? Then again, it's optimization, so it means a trade-off. Don't use conditional move if your if block is like 10,000 lines long, right? So if you have a big if, big else, like that consists of tens of lines, don't use conditional move, use a jump instruction. Otherwise, you'd have to repeat amount of work. It's gonna be longer. It's gonna be slower. Don't do it if the if has things like exception handling, or it can cause exception, or it can do like printf or scanf. And the other, basically, if one of the if or else has what we call side effects, right? Side effects. Most of the time, you don't have to worry about this. Why do I bring it up then? Right? You might be wondering, why do I bring it up? Because GCC and other compilers love to do this, because they love to do this. So you can see, right? You can see these optimization that GCC did, right? That turns, right? You turn your if else to C move, the conditional move. So be aware that if you see C move, it's likely to be one of your if else in the C code that get converted by the compiler, right? So that's why I want to bring it up, because it can come as a surprise to you. It's like, wait, what happened? I don't have this, right? A lot of time when you look at the assembly code that you compile, it would look totally different from the program that you've written. So it's good to be aware of some of the tricks that the compiler tried to do, because it does help understanding what's going on with your program, especially when it's buggy, right? All right, so that ends the lecture portion today. Before we leave today, we have one more in-class exercise for this is a practice for your assignment 3. The exercise is asking you to compute what we call parity bits. The concept of parity bits is used in many basically application of computer science, including security and any many things that would deal with error correction and how to detect if there's any error in your data. So it is actually one of the more common operations that if you work in certain area in computer science, you would need to use this a lot. We ask you to compute the parity bits. And the way it works is simple. Let's say you have one number. What you do is convert to a binary, like 11001. Then the parity bit of this is to count the number of ones. If there are even number of the ones, the parity bit is 0. If there's an odd number of the ones, the parity bit is 1. Yeah, that's it. Just find if there's even number of ones or odd number of ones, then that's the result. It should be really simple. Feel free to use any logical operation, loop, and branches, and that's it. All right. So that's for the in-class exercise. I hope to see you on Discord session, because I know that the homework is due tomorrow. All right. So if you have questions about assignment 2, feel free to let me know. If you want to work on in-class 9, feel free to let me know about any questions. I'm gonna conclude the recording right now, and then